In numerical linear algebra, the Jacobi method is an algorithm for determining the solutions of a diagonally dominant system of linear equations. Each diagonal element is solved for, and an approximate value is plugged in. The process is then iterated until it converges. This algorithm is a stripped-down version of the Jacobi transformation method of matrix diagonalization. The method is named after Carl Gustav Jacob Jacobi. Description: let be a square system of n linear equations, where then A can be decomposed into a diagonal component D, and the remainder R. The solution is then obtained iteratively via where is the kth approximation or iteration of n is the next or k plus 1 iteration of. The element-based formula is thus: the computation of xi requires each element in X except itself. Unlike the Gauss-Seidel method, we can't overwrite xi with xi, as that value will be needed by the rest of the computation. The minimum amount of storage is 2 vectors of size n. Algorithm: choose an initial guess to the solution while convergence not reached. Do for I equals 1 step until n. Do for j equals 1 step until n. Do if ji then end if end. Check if convergence is reached. Loop convergence. The standard convergence condition is when the spectral radius of the iteration matrix is less than 1. A sufficient condition for the method to converge is that the matrix A is strictly or irreducibly diagonally dominant. Strict row diagonal dominance means that for each row, the absolute value of the diagonal term is greater than the sum of absolute values of other terms. The Jacobi method sometimes converges even if these conditions are not satisfied. Example: a linear system of the form with initial estimate is given by we use the equation, described above, to estimate. First, we rewrite the equation in a more convenient form, wherein. Note that wherein are the strictly lower and upper parts of. From the known values we determine as further is found as within calculated, we estimate as. The next iteration yields. This process is repeated until convergence. The solution after 25 iterations is another example. Suppose we are given the following linear system. If we choose as the initial approximation, then the first approximate solution is given by using the approximations obtained. The iterative procedure is repeated until the desired accuracy has been reached. The following are the approximated solutions after 5 iterations. The exact solution of the system is an example using Python and NumPy. The following numerical procedure simply iterates to produce the solution vector. Import NumPy as np iteration underscore limit equals 1000 hash. Initialize the matrix A equals np dot array hash. Initialize the RHS vector B equals np dot array hash. Prints the system. Print for I in range. Row equals asterisk x. Format for j in range. Print equals b I. Print for it underscore count in range. Print x underscore new equals np zeros underscore like for I in range. S1 equals np dot dot S2 equals np dot dot x underscore new I equals a I if np dot all close. Break x equals x underscore new. Print error equals np dot dot b. Print produces the output. System 10.0 asterisk x1 plus minus 1.0 asterisk x2 plus 2.0 asterisk x3 plus 0.0 asterisk x4 equals 6.0 minus 1.0 asterisk x1 plus 11.0 asterisk x2 plus minus 1.0 asterisk x3 plus 3.0 asterisk x4 equals 25.0 2.0 asterisk x1 plus minus 1.0 asterisk x2 plus 10.0 asterisk x3 plus minus 1.0 asterisk x4 equals minus 11.0 0.0 asterisk x1 plus 3.0 asterisk x2 plus minus 1.0 asterisk x3 plus 8.0 asterisk x4 equals 15.0. Current solution 0, 0, 0, 0. Current solution 0.62.27272727 minus 1.1 1.875 current solution 1.04727273 1.71590909 minus 0.80522727 0.88522727 current solution 0.93263636 2.05330579 minus 1.04934091 1.13088068 current solution 1.01519876 1.95369576 minus 0.96810863 0.97384272 current solution 0.98991322.01141473 minus 1.01028591 1.02135051 current solution 1.00319865 1.99224126 minus 0.99452174 0.99443374 current solution 0.99812847 minus 1.00197223 1.00359431 current solution 1.00625131 1.99867003 minus 0.99903558 0.99888839 current solution 0.99967415 minus 1.00369161 1.00611919 current solution 1.001186 1.99976795 minus 0.99982814 0.99978598 current solution 0.99942422.0008477 minus 1.00068333 1.001085 current solution 1.00022141 1.99995896 minus 0.99996916 0.99995967 current solution 0.99999732.0000158 minus 1.0001257 1.0001924 current solution 1.0000409 1.99999268 minus 0.99999444 0.99999925 current solution 0.99998162.0000292 minus 1.0000233 1.000000344 current solution 1.0000075 1.99999868 minus 0.99999899 0.99999862 current solution 0.99999672.0000054 minus 1.0000042 1.0000062 current solution 1.0000014 1.99999976 minus 0.99999982 0.99999975 current solution 0.99999942.00001 minus 1.0000008 1.0000011 current solution 1.0000003 1.999999996 minus 0.999999997 0.999999995 Current solution 0.999999992 2.0000002 minus 1.0000001 1.0000002 Current solution 1.999999999 minus 0.999999999 0.999999999 Current solution 1, 2, minus 1, 1 Solution 1, 2, minus 1, 1, error, minus 2.814401007 E08 5.15706873 E08 minus 3.634663559 E08 4.17092547 E08 Weighted Jacobi method. The weighted Jacobi iteration uses a parameter to compute the iteration as with being the usual choice. Recent developments. In 2014, a refinement of the algorithm, called scheduled relaxation Jacobi method, was published. The new method employs a schedule of over and under relaxations and provides performance improvements for solving elliptic equations discretized on large 2- and 3-dimensional Cartesian grids. The described algorithm applies the well-known technique of polynomial acceleration to a problem with a known spectrum distribution that can be classified either as a multi-step method or a one-step method with a non-diagonal preconditioner. However, none of them are Jacobi-like methods. Improvements published in 2015